Let's explore the geometric mean. First, what is a mean? A mean is an average, or a middle ground between two things. But we have more than one way we can find a middle ground. The most common is an average, where we add together two objects and divide by 2 to find their midpoint. Say $5 and $15 adds together to $20. We divide by 2, we get $10, and $10 lives halfway between $5 and $15. Averages deal with objects that are laid out in one dimension. Geometric means deal with objects laid out in two dimensions. At least that's the way I like to think about them. To extend our analogy here, we can also take an average of three objects. So we'd add all three together and divide by 3. Now, a geometric mean, by contrast, is raising the complexity of the operation by 1 degree. Addition, we could say, is one of the simpler things that we can develop. But multiplication is closely related. Multiplication is just adding the same thing over and over and over again. So multiplication is repeated addition. Similarly, square roots are repeated divisions. So if an arithmetic mean is adding two things together and dividing by 2, then a geometric mean is going to up that operation and multiply two things together, and then analogously undo it by something divide 2-ish, but at a two-dimensional level. And a square root is the perfect object there because it's the thing that says, let's consider an area and where do the sides come from. So one of the most beautiful intuitive ways to think about what a geometric mean is explaining is it's saying, if you construct an area by A and B, you multiply them together to get a shape. Now you've got an area, that's A times B. Taking the square root amounts to asking, how does that area relate to a square of equal size? And what would the side length of that square be? So a rectangle of sides A and B is equivalent to a square of sides AB. One of the classic problems from antiquity. What does it mean to be able to square an object? So you might hear the expression at some point, square a circle. The idea there is to say, can we geometrically construct and define what it means to take the area of a circle and redefine it as a square with exactly the same area? Very complicated problem in geometry. Okay. And geometric means, again, have their analog in higher order. So we can take three things and multiply them together and take their cube root. And this is a three-dimensional version. So if this one is in 2D, then this one over here is living in 3D, where we can build a shape that is A by B by C, that would be a volume. And we could ask, what is the equivalent shape that's going to be a perfect cube? And the side length of that cube would be the cube root of ABC. So let's handle this with geometry. Let's dig a little deeper on this. And this is going to be a multi-stage proof that we're going to go through here. I'm going to start with something that is a classic that perhaps you already know about and prove it in two different ways, and then lead up to where's the geometric mean hiding in there. So my challenge to you as we go along is to see if you can spot the geometric mean before I lay it out. And it'll be a little while because we've got to go through the proving first. So here's the diagram we're going to be playing with, and we'll come back to this page. We're going to consider a half circle. We're going to consider a point on that half circle, and we're going to construct a triangle that goes across the diameter as the hypotenuse and connects to the point. And I claim, and perhaps you already know, that this triangle is in fact a right triangle. I'll go ahead and label the different sides of this in some ways. and we will build ourselves up to understanding where the geometric mean is living in here. Now, a couple other key features that I'm going to play with as we go along here is I'm going to end up looking at the altitude in that triangle if we drop down to get that. And I'm also going to look at the line to the center of the circle and define the radius r. Now, first and foremost, how can we prove that this is a right triangle? Well, perhaps the most obvious and classic definition that everybody can think about is the Pythagorean theorem. So I have the hypotenuse down here, and I have side 1 here and side 2 here. Perhaps I can show that side 1 squared plus side 2 squared is equal to the diameter, or the hypotenuse squared, which is going to be 2r squared. Okay, I can do that. And I'll do that with some distance formulas. But before I can use distance formulas, I need a coordinate system. So the last thing I need to add to my diagram is where am I going to define the origin? And I know, and perhaps you know already, that circles are easiest to define in a Cartesian coordinate system if they're centered at the origin. So I'm going to go ahead and put my xy axis right here. That lets me label now the vertices of my triangle with points. So the one at the top here is arbitrary. It's somewhere along the curve. It happens to be along a circle, so I do know some things about it. I could call it x squared, y squared. I can remember that a circle has the equation, is if it's centered at the origin, of x squared plus y squared equals r squared. And in our case, r squared is going to be r squared, CC. And that would mean that this point over here is going to be r0, and this point over here is going to be negative r0. Gives me those pieces to play with. All right, so let's get straight into the Pythagorean theorem for proving this. We already have a definition for the hypotenuse of the triangle. Our 2r squared is straightforward, it's good. But what are we going to call S1 and S2, and how are those going to work? Before we get to the next page, I think you put that in right here. S1 is this distance right here, and it itself is defined via the distance formula as a Pythagorean triangle. We're going to be taking this right angle down here for this hypotenuse, for this altitude that I dropped, and say, hey, the base of that is something, the height of that is something, and the long diagonal is something. So we can define that. So the distance along the bottom here is going to be r units from the origin to the point, and then a further x units to my coordinate point. I could label this guy down here if we'd like as well. It'd be x0. So I'm going to have x plus r squared is the base, and then the vertical here goes from 0 up to y, so the distance here is going to be y, so it's going to be y squared. And similarly, S2 squared, using the Pythagorean theorem, is going to say, hey, the base here is going to be the entire distance r less the distance x. So r minus x squared, and again, same vertical distance, y. So if we want to prove that this is a right angle, we want to justify that this equal sign makes sense. Well, now we have a definition for S1 squared and S2 squared, coming from the Pythagorean theorem, and we can add their definitions together and see if we do in fact get 4r squared. So let's go ahead and do that. So r plus 1 squared plus y squared plus r minus 1 squared plus y squared equals, instead of foiling this out, r squared plus 2rx plus x squared plus y squared, and r squared minus 2rx plus x squared plus y squared. We're going to get 2 copies of r. We're going to get those conveniently canceling each other out. We're going to get 2 copies of x and 2 copies of y squared. And remember, this whole time we've been asking ourselves, does that in fact equal this? So can I make a claim about this being the same as 4r squared? Well, it looks like I have some rearranging in my path ahead of me. So if I subtract a 2r squared from each side, I've got x squared, 2x squared plus 2y squared equals 2r squared. And what do you know? The simple divide by 2 will pull all those 2's off, and we are up here matching this. And what does that prove? This tells us that in order for this equal sign to be true, because I assumed it was when I subtracted 2r from both sides, in order for this equal sign to be true, the coordinate point xy must satisfy this resulting equation, must exist on a semicircle. And so now we've officially proved that piece of geometry that has been in the playbook for ever so long. Again, if it's new to you, great, I'm teaching you something amazing. If it isn't, let me just remind you that this is true all the time for any circle and any point on that semicircle. Oops, what am I doing there? If you connect the endpoints of the circle to the point in the middle, wherever that point in the middle may fall, left or right, you will always get a right angle. And we've just proven that. So that's my first option for that. Let's prove it another way. I'm going to teach you about vectors. Again, we have a semicircle. This time, we're not going to need a coordinate system. So this is useful in its simplicity. Instead, I'm going to define vectors from the origin in the direction u and the direction v and the direction negative u. A vector is an object that has a direction and a distance associated with it. So they're like driving directions. Starting from here, head this far at 30 degrees rotation from west. Something like that. So that's what these 3 vectors are. So vectors get arrowheads to describe them. And you can do interesting things with vectors. You can add them together, you can subtract them, you can do different objects with them. So one of the things that we have with vector subtraction is we can define a new vector that connects the tips together. And it has the rule of taking the terminal vector point, so it's going to be u, minus the beginning vector point, that's going to be v, to define that vector. So I'll define similarly a vector over here. So it'll be somewhat longer. The terminal point would be negative u, and the vector would be v. So this one will read negative u, take away v. And now I have this vector and this vector that complete my triangle. Now there's a third vector rule called the dot product that helps measure the angle between 2 vectors. So we want to consider that area or that angle up there and see if it is in fact 90 degrees. So to do that, we're going to take the dot product between negative u minus v and u minus v. The dot product measures the magnitude of u times the magnitude of v times the cosine of the angle in between them. And for our purposes, we don't need to worry about all of that detail. This is too much. The clean takeaway from there is if that is in fact 90 degrees, we know that the cosine of 90 degrees is 0. So who cares what u is, who cares what v is? We're going to get a 0. So that is what we're seeking to find. Now, the other thing we do have in our toolbox that is not declared explicitly, but you can see it in the diagram, is that the magnitude of u is going to have to equal the magnitude of v, is going to have to equal the magnitude of negative u for multiple reasons. And that's because these are all radius vectors from our circle, so they have to be the same distance or it wouldn't be a circle. So we get to have that fact as well. And we'll see where that comes in here. So let's go ahead and carry out the dot product. It follows the same rules as foiling. So we're going to get negative u dot u, negative u dot negative v, negative v dot u, and negative v dot negative v. And that's just saying I'm going to take the first object times the first object, the first times the second times the first, and the second times the second. And I get all 4 of those combinations. Now, consider each of these in turn. U dot u is nothing more than the magnitude of u squared. Negatives cancel each other out, and this is u dot v. This is negative v dot u, and again, negatives cancel out, and this is nothing more than the magnitude of v squared. But we know that the magnitude of v is actually the same as the magnitude of u, so we can make a substitution there. And we know that dot products compute the same either way. They're symmetric, so this could just as readily be rewritten as u dot v. Copy these 2 guys down. Oops. And what do we got? We've got this first term cancels this term, and the middle 2 terms cancel each other, and we do in fact get a 0. So we've proven that. Okay, so now that's 2 different ways that we've proven that this angle is 90 degrees. Now we can look for the hiding geometric mean. And let me redraw attention to the first method that we proved this by, where in the process we also built up that altitude, right? Recall we had the altitude drop down right there, and we used that when we defined the base lengths for computing S1 and S2. Well, let's keep playing with those. We'll take a slightly different approach on them. Our next goal in our journey to the geometric mean is to prove that the triangles that we've been playing with are actually all proportional to each other. So again, back to our main drawing. This time I'm going to label this base A and this base B and the altitude C. And then of course I still had side 1 and side 2. And the analogy I wanted to point out here is one of similar triangles. I claim that the big triangle that we've been proving that is 90 degrees is actually exactly the same kind of triangle by shape as the triangle ACS1 and as the triangle BCS2. And let's see if we can go ahead and prove that. So one way to prove that triangles are similar is to show that they have all the same angles. So let's go ahead and call this angle up here alpha and this angle up here beta. And that's just following the convention that we want to name opposite sides with matching labels. So alpha and A go together, and beta and B go together. Well, what does that mean? Alpha and beta up here, we can see, have to add to 90 degrees. But then if we look at this triangle right here, we already have 90 degrees right here, and we know that all of the angles in a triangle must sum to 180. So if 90 is used up and alpha is used up, then the only option for this angle over here is going to be beta because it has to be the complement to alpha. Similarly, this has to be alpha because it has to be the complement to beta. And again, we have a 90-degree angle right there. So we have one triangle with angles beta 90 degrees and alpha, another triangle with angles beta 90 degrees and alpha, and a third triangle with angles beta 90 degrees and alpha. So all the triangles are similar to each other. We can say that triangle, we'll get our order right on these ones. I'm going to go with short, medium, long. So for the big triangle, I would say triangle S2, S1, and A plus B is similar to triangle CAS1 is similar to triangle BCS2. That way I'm always matching up sides that are analogous to each other. Right? So great, I have that. Fantastic. Now, where is this finally going to get me down to the end? Well, analogous triangles have proportions on their sides, one of the simpler linear kinds of analogies. So amidst that, we can say things like short side is to long side in, I'll move it over here. Short side is to long side in this triangle, as short side is to long side in all the other triangles. So short side to long side here would be B over C. Short side to long side here would be S2 over S1. And those are all going to be equal to each other. Now, I could play with any of those, but actually this is the pair I want to care about. If I rearrange this a little bit, I can say that C squared is equal to AB. And so I can say that C is equal to the square root of AB. And there's my geometric mean. Did you see it hiding in there? So let's draw our final version of the picture where we can see where exactly this is lurking. This height right here, C, is the geometric mean of the two components it's made out of the distance A and the distance B. So if I want to lay that out in mathematical terms to see something truly beautiful, I can rotate a copy of B down here. And this lets me construct this rectangle, which has area A times B. At the same time, I could take a copy of this altitude of this triangle and rotate it down to get a distance defined from here to here as being a second copy of C. And that would let me define this square, which is C by C. So what a geometric mean is doing is it's telling us how to square a rectangle. It's giving us a method by which we can take this easy enough to compute area where we just pick two arbitrary numbers, multiply them together and get a rectangle. It's telling us how to transform that oblong rectangle into a nice surface area or perimeter conserving square. And the 3D analogy works as well, and beautifully, and a little complicated for our brains. The 4-day analogy would also work. You can take a geometric mean of 4 objects and find the side length of a hypercube if you like. Thanks for listening.